Next, we're going to see how we can use the derivative to come up with a couple of useful approximations. The first one is called the linear approximation, or you could call it the tangent line approximation. So here's the setup. We have some function, and I'm going to label a point A and a point X, and of course we have corresponding points f of A and f of X, the y values. Now, what we want to know in this example is this y value. We want to know f of X. We do know, and in the examples we will know, a certain value close to X. I'm going to call it A. We know exactly how to find this point. We know everything we want to know about this point. What we want to know is information about that point. One thing we can do to approximate this y value is consider a tangent line at A. So what would that look like? A tangent line at A would look like that. And since we know everything about what happens at A, we can easily find that tangent line using the derivative. And what we're going to use to approximate this point is this point on the tangent line at X. So let's write that down. This point on the tangent line, right there, we can find that point. We can find an equation for the tangent line, so we can find this y value corresponding to that given x value. And what we will find is that this point will give a reasonable approximation for f of X. Meaning, we can find this y value quite easily using the tangent line, and we're going to use that to approximate the y value we want, which is on the curve. So notice this is an approximation, so there is a difference between the actual f of x value and the f of x value we'll find using the tangent line. But our goal here is to use the derivative to find an approximation. So let's define this point more formally. Well, let's define this line more formally. So right here, this first remark, we may, let's call it a remark. This remark summarizes what I just said. We may approximate f near A using the line tangent to f at A. And right here is just turning that sentence into math. F of X is approximately equal to f of A plus f prime of A times x minus A. And that is, if this were equal, then that would just be an equation for the tangent line. But remember, we're using that to give this approximation point at X. So right here, this f of X is actually this y value. And this equation says that this y value is approximately equal to f of A, so this y value, plus the derivative times a change in x. So I like to think of that as f of x is approximately equal to this point plus a little bit more using the derivative. And this is found from the tangent line. You can see that it is actually just another rearrangement of the equation for a tangent line, because we'd have f of x minus f of A equals the derivative times x minus A. So that's a point slope form where the one y value is moved to the other side. So as a definition, we're going to define, the goal here is to define something called the linear approximation, because that's in general what we are doing. So we're going to call this function right here a new function. We're going to call it capital L of x. We're going to define this new function as f of A plus f prime of A times x minus A. We're going to call that the linear approximation or linearization of f at A. And right here, this f of x just gives you a specific value. This function, linearization, L of x, gives you all values. So you can put any x in here, and up here this is just approximating a certain y value. So let's do an example. Let's see, what example? Find the linear approximation of this function, square root of x at a equals 9, and use it to approximate the square root of 9.1. So find the linear approximation of f of x is root x at a equals 9. That means find that function L of x and use it to approximate a certain value. Notice we're using it to approximate something close to 9. These approximations will give us reasonable approximations when we're approximating near, when the approximation we want to find is near a point we know. So if this said, if this just said approximate square root of 9.1 using a linear approximation, you wouldn't want to use a equals 4, because 4 and 9.1 are far away. So here we're going to use a equals 9, because 9 and 9.1 are kind of close. So what we want to find is the linear approximation. So L of x is what? F of a plus f prime of a times x minus a. So what we need is our function. We need the derivative. We have f of x is root x. F prime of x, I'm going to use the, so you could write it half x to the negative half, but we're going to eventually have to substitute. So when we have to substitute, I'd like to just write it as 1 over 2 root x. So once we have the function and the derivative, all we have to do is substitute. Now notice, what we're substituting here, we're going to be substituting a into this. What we are substituting into these functions is the value we know about. So in that, before we define linear approximation, I said we know what happens at a. So here for this square root function, we know the square root of 9. So that's a good point to choose. We don't really know the square root of 9.1. We're approximating that. But we do know the square root of 9. And we're going to use that to approximate square root of 9.1. So I guess I'll just write this like this. So f of a, f of 9, I should say. F of 9 is square root of 9, which is 3. And f prime of a is 1 over 2 root 9, so 1 over 2 times 3, so 1/6. And now we can find the linear approximation. So L of x equals f of a, 3 plus a 1/6, times x minus a times x minus 9. That's not a good 9. X minus 9. And I mean, notice this function is a line. It's a line with slope 1/6, intercept something else. You could simplify this if you want, make it a 6x minus 3 halves, and then make it what, a 6x plus 3 halves. I'm okay with it in this form. I actually think this form is more useful for what we're doing. Because right here, this shows us a lot. This shows us that we're approximating starting at 3. And this equation right here tells us that square root of 9.1, which we'll eventually find an approximation for, square root of 9.1 is going to be close to 3. And then it's 3 with this kind of adjustment, a 6th times x minus 9. So I like this form. If you simplify, you won't lose points. So right here we've found the linear approximation. Now we have to approximate square root of 9.1, which I'll do over on this board. Approximating square root of 9.1 is just finding L at 9.1. So L at 9.1 equals 3 plus a sixth times 9.1 minus 9. No calculators here. You do not need a calculator here. 3 plus a sixth. 9.1 minus 9 is a tenth. So you have 3 plus 1/60th. And I also am okay with this answer written like that. You could write it as, what, 181 over 60 if you want. I like this answer more, because it tells you the answer is 3 and then a little more than 3. But you could write it as 181 over 60 if you want. So notice one thing about this. In this approximation, the answer we found does take the form of what we would expect it to be. We would expect this approximation to be, or we would expect the square root of 9.1 to be a little more than 3. So we should expect our approximation to give us a number a little more than 3, and it does. Let's do a second part on this example. Let's not yet, because I just wrote in my notes the exact value. I'll just write this over here. I should write it over there, but I don't have room over there. So I'll just note, using a calculator, the square root of 9.1 is approximately 3.016620, and so on. So the actual square root of 9.1 is 3.016620. 181 over 60 is approximately 3.0167. So you can see that this approximation is actually quite close to the actual value. Let's do a second part, or well, a second example. Instead of approximating square root of 9.1, let's approximate the square root of 8.99. So we'll have the same directions, except we're going to approximate square root of 8.99. So finding the linear approximation is the same. We would get this function. But now we're going to use that to approximate the square root of 8.99. I'll erase this since it's written over there. So let's find the square root of, or let's approximate the square root of 8.99. Let's do it on this second board, actually. So we want L at 8.99, and that equals 3 again plus a sixth times 8.99 minus 9. And what do you get? You get 6, you get 3 plus a sixth. 8.99 minus 9 is negative 0.01, which is also known as negative 1/100th. And just simplifying that, you get 3 minus 1 over 600. And I guess if you want, you could simplify that to, what, 1799 over 600. So we've approximated that using the same linear approximation. We found an approximation for the square root of 8.99. Now, one thing I'd like you to notice, and some of you may have already noticed this. I'm going to get rid of the actual numbers. They're just going to be in the way. That one has a negative sign. This one has a positive sign. That is expected, because in this one we were approximating something larger than 3. Larger than square root of 9, I should say. In this one we're approximating something smaller than the square root of 9. So we should expect the answer to be 3 without something. And you can see that the negative shows up from this x minus a term. In both cases, the negative shows up. So in the formula for linear approximation, this is a positive sign. But here, a negative shows up. Let's do another. I shouldn't have erased those directions because I'm just going to have to rewrite all of them. Actually, I won't. I'll be able to summarize them a little. So let's do this example. Using a linear approximation, approximate the log, natural log, of 0.9. There should be a period at the end of that sentence, but I won't put that there now. Using a linear approximation, approximate log of 0.9. So right here, I'm not telling you where to start your approximation. Now, it does say log of 0.9, so you might suspect that we should do our approximation near log of 1. And can we do that? Is log of 1 a value we know? What is log of 1? E to what equals 1? E to 0 equals 1. So log of 1 is a value we know. Could have also used the graph. Log of 1 is 0. So we will find L of x near a equals 1, because we know log of 1. So let's find that. Well, f of x is log x, so f prime of x is 1 over x. Well, in our linear approximation formula, we need f at, in this case, 1, and f prime, in this case, at 1. F prime at 1 is 1 over 1, which equals 1. F of 1 is log of 1, which equals 0. And I'm going to write that a little smaller so I have the rest of that board for the actual answer. So f of 1 is log of 1, which equals 0, because e to the 0 is 1. Well, we have all of the numbers we need. Now we just need to find the linear approximation. So L of x, when I'm doing this, I flip between the cursive L and the non-cursive L. They are the same. I just, I don't know. Sometimes I like using this. Sometimes I like using that. I don't think too much about it. But L of x, so it's f of 1, which is 0, plus f prime of 1, which is 1, times x minus 1. Now this one does simplify nicely. It does just simplify to x minus 1. So here I am going to use the simplified form just because that was easy enough to simplify with the 0 and the 1. Well, we found the linear approximation. Now we need to approximate log of 0.9. So log of 0.9 is approximately equal to, it's approximately equal to L at 0.9, L at 0.9, and L at 0.9 is L with 0.9 substituted, so that's 0.9 minus 1, which is negative 1/10. You could say negative 0.1 if you want, but I won't. Let's do one more of these linear approximations. Let's do a cube root. So with these cube roots, we need to know our cube roots. So what's 1 cubed? 1 cubed is 1, 2 cubed is 8, 3 cubed 27, 4 cubed 64, 5 cubed 125, 6 cubed, whatever that is, 216 I think. Let's approximate the cube root of, what's a good number? I wrote 28 in my notes. I don't want that. Let's do 27.2. Let's do let's approximate this cube root of 27.2. So again, I didn't tell you where to start here. So you need to figure out what is the cube root of 27.2 close to. Well, the cube root of 27.2 is close to the cube root of 27. So we will find the linear approximation near a equals 27. So let's do that. Well, our function, f of x, is the cube root of x, which is x to the 1/3. So f prime of x, and here I will just do the third x to the negative 2/3. But I will simplify that. Will I? I don't know. Should I simplify it? No, let's just leave it like that, I guess. Now let's simplify it. I don't know. I don't know if the simplified version is easier to do the computation. Well, whatever. Let's leave it like that. So we need f of x. So we need f of x at 27. Is 27 is the cube root of 27. F of 27 is the cube root of 27, which is 3. So f prime at 27 is 1/3 times 27 to the negative 2/3. What's 27 to the negative 2/3? Well, we have some sideboard over here, so let's do 27 to the negative 2/3. How do we do? Well, let's just do to the 2/3 right now, because the negative will just throw it in the denominator. What's 27 to the 2/3? Well, 27 to the 2/3 is the cube root of 27 squared. What's 27 squared? I don't know, it's 3 to the 6th. What's 3 to the 6th? I think it's 729, but that doesn't matter. We don't have to do that. It is 729, because 9 to the 3rd is 729. What we can do instead is take the cube root of 27 and then square it. And that's easier to deal with because the cube root of 27 we already know is 3. And 3 squared is 9. You could also say 27 to 2/3 is 9 because, you can count by multiples of 3, or not multiple, you can count by powers of 3. 3 to the 1 is 3, 3 to the 2 is 9, 3 to the 3 is 27, so 27 to 2/3 is 9. So we have 27 to the 2/3 is 9. Well, that's great. We need 27 to the negative 2/3. 27 to the negative 2/3 is 9 flipped around. 9 flipped around is 1/9. So f prime at 27 is 1/27. And now we can find our linear approximation. So L of x is f of x, the starting point, 3, plus the derivative, 1/27 times x minus the starting point. So that's times x minus 3. And I'm not going to simplify that. So right here, I'm just going to write is just to clear off this board so I can finish the answer over here. We'll just change that 1/3 times 1/9, which is 1/27. So we want to approximate the cube root of 27.2. So the cube root of 27.2 is approximately equal to the linear approximation at 27.2, and the linear approximation at 27.2 is 3 plus 1/27 times, oh, what am I doing? I made a mistake. What am I talking about? This isn't at the starting point over here. That's times x minus the value you're making your tangent line on, because it's the x value for the tangent line. X minus 27. And why did I catch myself? Why did I catch that error? It's always good in math to know why you catch your errors. If I left that as 3, this would have been 27.2 minus 3. I know with these, we're not going to have to deal with numbers like that, because it's not set up to make us deal with numbers like that. It's set up to make us deal with smaller numbers. So where was I? 1 plus 1/27 times 27.2 minus 27. So what does that equal? 3 plus 1/27. So here we have 2/10. So you could say times 2/10, but then you'd have to reduce that. So I'll just say times 1/5. So that's 3. So I'll say equals 3 plus 1 over 135. And I'll leave the answer like that. You could make it, what would that be? 406 over 135, I guess? Yeah. But I'll leave it like that. So 27 times 5. How do you do 27 times 5? How do I do 27 times 5? Well, I don't go 27, 54, 81, 108, 135. 27 times 5, what I do is I take half of it, 13 and a half, and then I multiply it by 10. So dividing by 5 is the same as throwing a 0 on it and dividing by 2, or dividing by 2 and then throwing a 0 on it. Well, throwing the decimal place over, I guess I should say. Or you could write out the multiplication on the side. So these linear approximations, finding the formula is a good deal of the work, but we will have a little bit of simplification as well. The next type of approximation we'll do is approximation by using what are known as differentials. So here we have a similar setup to the linear approximation. We have a curve, we have a point A, and here I'm going to change this other x value to a plus dx. In these examples, it'll be useful to think about this entire distance between a and this value as just being some sort of change in x. So right here, if this x value is a, and this x value is a plus dx, then this entire piece is going to be dx. This entire piece between those two vertical dotted lines is dx. And we're going to define this dx to be delta x. So we're going to have a dx, a lowercase dx, so that we can interpret this, well, so that our interpretation using derivatives is useful, and delta x because that's what we usually do for a change. So here we have a change in x, delta x, and we're going to call that dx. Delta x and dx are the same. Well, that's great. We have a, we have another x value called a plus some change in x, and right here our goal again is going to be to approximate this value on a given curve, which we call f. And again, we know what happens over here. And we're going to again approximate this change in y. So why is that the change in y we want? Well, this change in y, delta y, is the difference between the y value corresponding to the point we know and the y value corresponding to the point we want to know. So we're going to define that to be delta y. And we're going to use this tangent line again to find an approximation for delta y. So right here we have this tangent line. The point over here we will be able to find because we'll be able to find the tangent line. We're going to define this distance that arrow should be over here. That vertical distance between the y value we know and the y value that we can find on the tangent line, we're going to call that dy, lowercase dy. And from this setup, we get a few equations that we will use. So I'll just say equations. First one, delta y equals f of a plus dx minus f of a. So delta y is the change in the y values. That's the change we're going to want to find. So it's f of a plus dx minus the y value here, so minus f of a. We can find dy using the derivative. And we can find it using the derivative and the change in x. Dy is exactly equal to f prime of x times dx, where dx is defined as this change in x. So this little y value here is found exactly using the derivative. Now, before I write the next equation, well, I'll just write the next equation. The result here with differentials that we'll use is that dy is used to approximate the change in y. So dy gives us an approximate change in y. Now, right here, this second equation, it looks like if you divide each side by dy dx, you get a nice equation relating two of our derivative notations. Now, this derivative notation does not act like a fraction. In fact, right here, we're on the xy plane. If we change ourselves to being in x, y, z three-dimensional space, and we look at the corresponding differentials result, we will not have that the derivative looks like it behaves like a fraction. But here, in Calc 1, this differentials result does allow us to think of, well, how should I say this? It gives us an example where we can think of the fractional derivative notation as being similar to a fraction. That sentence could have been said better. Let me try to say it better. With differentials, it is okay to think that these act like fractions. However, they don't actually act like fractions. So let's look at two examples. Let's erase this. I'm going to need those equations probably. This first equation, of course, is the same as f of a plus delta x, but we're going to use dx. Example. Find delta y and dy. So find these first two at x equals 3 if dx equals 0.1 using this function. So I'll just say for f of x equals x squared plus 2x. So find dy and delta y. And we'll see that they are actually close. Are they close? Let's see. Yeah, they're pretty close in this example. So find delta y and find dy. Well, let's find delta y first. Delta y equals f of a plus dx. Yeah, that should say a equals 3. Excuse me. A equals 3, not x equals 3. To remain consistent with that notation. So delta y is f of a plus dx minus f of a. So it's f of 3.1 minus f of 3. So let's find f of 3.1 minus f of 3. Oh, that's an annoying computation, but that's okay. We can handle it. F of 3.1, so we have 3.1 squared. What's 3.1? 3.1 is 31/10. Is that how I did this? Oh, no, okay. That's how I did it. I used a calculator because I didn't want to do 31 squared. So I'm going to tell you this result. On a test or a homework, if you are required to do one of these, maybe 1.1, you can do 11 squared, 121, but 31 squared, what is it, is it 961? Yeah, it's 961. I won't have you deal with that. I'll just tell you this answer is 0.81. 0.81 if you go through that computation. And what's dy? dy equals f prime of x dx. What's f prime? F prime of x is 2x minus 2. So f prime at 3. So f prime at 3 is 6 minus 2, which equals 4. Okay, that's... okay, That should be a positive 2. I was going to say that answer's not close. That should be a positive 2 down here. So it's 6 plus 2, which is 8. That's better. So f prime of x equals 8 times dx. dx is 0.1. So here we get 0.8. So you can see with this example, dx and delta x are quite close. Let's look at the second example. Now, in this example, suppose the side length of a cube is measured to be 5 inches with a maximum error in measurement of 0.1 inches. Approximate the maximum error in volume. So right here we know that the volume of a cube is related to the length of a side of a cube. So right here we can use differentials to see how much, to approximate how much of an error in the volume will result from an error in measuring a side of a cube. So right here we need volume of a cube in terms of side length. Volume is x cubed. All we need to do is find the differential. So here the differential, dv, is going to be exactly equal to 3x squared dx. And that's how we will write that. I think that's the easiest way to write that. So dv is exactly equal to that. It's not approximately equal to this. The actual error is approximately equal to it. But remember, from the third equation over there, the approximate error, or the exact error, is approximated by this differential. So 3x squared, what's x? 3 times 5 squared times the error. The error is 0.1. So what do we get here? We get 3 times 25 divided by 10, so 3 times 25 over 10, which is 75 over 10. So you could say 7.5, or you could say 15 over 2. So I'll say or 7.5. So this is definitely more likely to be asked of you something like this than that first example. That first example was really just to illustrate how dx, or how dy approximates delta y, which is why I just gave you that first number without going through the computation. So try these 2 approximation methods. There are a couple examples on the homework and in the worksheet. See how they go. There is one of these in the worksheet with a cylinder that's a good deal harder than this one, I think. It's a good one to know. It's a good one to look over.